Let us begin our journey into the cosmic embrace. As you settle into a comfortable position, feel the gentle rise and fall of your chest with each breath. Imagine each exhale carrying away the tensions of the day, and each inhale drawing in the peace of the cosmos. We are about to embark on a voyage across space and time, a journey that will carry us from our familiar blue planet to the farthest reaches of the observable universe. Throughout this journey, remember that you are part of something vast and beautiful, a universe that has been evolving for nearly 14 billion years and now produces beings capable of contemplating its majesty. Let this thought comfort you as we begin our exploration. Our Earth floats in the perfect balance of the circumstellar habitable zone. This Goldilocks region, where temperatures allow liquid water to persist, is just one of many conditions that make our world so special. The planet's substantial iron core generates a protective magnetic field. This invisible shield deflects the solar wind's charged particles, preventing them from stripping away our atmosphere, while creating the magnificent auroras that dance near the poles. Earth's atmosphere itself is a marvel of chemical engineering. Nitrogen provides stability, while oxygen enables complex life. Trace gases like carbon dioxide maintain our delicate greenhouse effect, keeping temperatures within the narrow range life requires. Our planet's rotation gives us the rhythm of day and night, a 24-hour cycle that has shaped all terrestrial biology. While the axial tilt of 23.5 degrees, the moon stabilizes this tilt against gravitational perturbations, preventing the climate chaos that would otherwise occur. Our lunar companion also creates the ocean tides that have shaped coastlines and influenced evolution. As you breathe tonight, consider the extraordinary convergence of circumstances that makes this pale blue dot such a welcoming home. In all our exploration of the cosmos, we have yet to find another world that matches Earth's nurturing embrace. Mercury stands as the solar system's innermost sentinel, a world of dramatic extremes and surprising complexity. Its surface is covered with vast, smooth plains and towering scarps, evidence of a global contraction as the planet's massive iron core cooled. The Caloris Basin spans 1,500 kilometers, a colossal impact feature surrounded by concentric mountain ranges. On the opposite side of the planet lies the weird terrain, a region of hills and valleys created by seismic waves, focusing through the planet's interior after the Caloris impact. Mercury's tenuous exosphere contains sodium, potassium, and calcium atoms, knocked from the surface by solar radiation and micrometeorite impacts. This ethereal atmosphere constantly escapes to space, but is continually replenished from the surface below. Despite its proximity to the Sun, radar observations suggest water ice persists in permanently shadowed craters near the planet's poles, where temperatures never rise above -170 degrees Celsius. These icy deposits may have been delivered by cometary impacts, preserved for billions of years in the eternal darkness. Venus presents us with a cautionary tale of runaway greenhouse effects. Its thick carbon dioxide atmosphere traps solar energy with frightening efficiency, creating surface temperatures hot enough to melt lead. The atmospheric pressure at the surface equals that found a kilometer deep in Earth's oceans. Yet Venus may have once been more Earth-like, with oceans of liquid water and a temperate climate. What transformed it into this hellish landscape remains one of planetary science's great mysteries. Recent studies of deuterium to hydrogen ratios in its atmosphere suggest Venus may have possessed substantial water in its past, perhaps enough to cover the entire planet in a shallow ocean. Volcanic outgassing may have released enough carbon dioxide to initiate a greenhouse effect that boiled away the oceans, leaving the desiccated world we see today. The Venusian surface shows evidence of relatively recent volcanism, with lava flows that may be less than 1,000,000 years old, and volcanic features unlike anything found on Earth. Coronae are circular crown-like structures hundreds of kilometers across, formed by upwelling mantle plumes that dome and fracture the surface. Tesserae are highly deformed plateau regions that may represent the oldest surviving terrain on the planet. Despite the hostile conditions, some scientists speculate that life might persist in the Venusian clouds, 50 kilometers above the surface, where temperatures and pressures approach Earth-like values. Here, mysterious dark patches that absorb ultraviolet light might indicate the presence of microbial organisms. Floating in the acidic atmosphere, Mars beckons with its rusty landscapes and promise of discovery. The planet's reddish hue comes from iron oxide minerals that coat surface rocks and dust particles. Massive volcanoes dot the Tharsis Bulge region, including Olympus Mons, the solar system's largest volcano. This shield volcano stands 21 kilometers high, with a base that would cover the entire state of Arizona. Valles Marineris stretches over 4,000 kilometers, a canyon system that would span the United States from coast to coast, with depths reaching 7 kilometers in places. Evidence of flowing water exists throughout the Martian landscape. Dried river channels, deltas, and lake beds tell of a warmer, wetter past, when liquid water flowed across the Martian surface. The Curiosity rover has found complex organic molecules in 3-billion-year-old mudstone, suggesting the building blocks of life were present on ancient Mars. Today, water exists primarily as ice in the polar caps and as subsurface ice deposits at middle latitudes. Liquid water may occasionally flow on the surface today, as suggested by recurring slope linea, dark streaks that appear and disappear with the seasons. The Martian atmosphere is thin, but dynamic dust storms can grow to envelop the entire planet, lasting for months and dramatically altering the climate. While at the poles, carbon dioxide frost comes and goes with the seasons, creating patterns of spiraling troughs and migrating sand dunes. Jupiter reigns as king of the planets, a gas giant whose mass exceeds that of all other planets combined. Its atmosphere displays a stunning tapestry of colorful cloud bands, rotating at different speeds and creating powerful jet streams. The Great Red Spot is an anticyclonic storm larger than Earth that has persisted for at least 300, though recent observations show it is gradually shrinking. Jupiter's composition resembles that of the early solar nebula, mostly hydrogen and helium with traces of other elements. Deep within the planet, pressure transforms hydrogen into liquid metallic form, creating a powerful magnetic field 10 times stronger than Earth's. This magnetosphere extends 7 million kilometers toward the Sun and stretches beyond the orbit of Saturn in the opposite direction. Jupiter's moon system resembles a miniature solar system, with 4 large Galilean satellites and dozens of smaller moons. Io is the most volcanically active body in the solar system. Its surface constantly renewed by hundreds of active volcanoes, powered by tidal heating as Jupiter's gravity flexes the moon's interior. Europa likely hosts a global ocean beneath its icy crust, containing twice as much water as all Earth's oceans combined. Tidal heating maintains this liquid water ocean, while chemical reactions at the seafloor might provide energy for life. Ganymede is the largest moon in the solar system. Bigger than the planet Mercury, it possesses its own magnetic field, and likely has a subsurface ocean sandwiched between layers of ice. Callisto shows the oldest surface in the solar system, heavily cratered and largely unchanged for 4 billion years. Evidence suggests it, too, may have a subsurface ocean, making all 4 Galilean moons potential habitats for life. Saturn's magnificent ring system spans 280,000 kilometers, yet averages only about 10 meters in thickness. The rings consist primarily of water ice particles, ranging in size from microscopic dust to house-sized boulders. Spiral density waves propagate through the rings, created by gravitational resonances with Saturn's moons, while propeller-shaped features indicate the presence of embedded moonlets. The Cassini division appears as a dark gap in the rings, but actually contains many thin ringlets with fine structure. Saturn's atmosphere appears more subdued than Jupiter's, but still exhibits banding and occasional large storm systems. The planet's low density means it would float in water. If such a colossal ocean existed, Saturn's moon Titan represents one of the most fascinating worlds in the solar system. It possesses a thick nitrogen atmosphere with surface pressure 1.5 times Earth's. Complex organic chemistry occurs in its atmosphere and on its surface, creating layers of organic haze that obscure the surface from visible light. Lakes and rivers of liquid methane and ethane dot the polar regions, while vast dune fields of hydrocarbon sand dominate the equatorial regions. The Huygens probe revealed a landscape remarkably similar to Earth, with hills, valleys, and drainage channels carved by liquid methane. Beneath the surface may lie an ocean of liquid water, making Titan another potential habitat for life. Enceladus surprised scientists. These icy plumes erupt from fractures called tiger stripes and contain water vapor, salt particles, and organic compounds. The material erupts from a global ocean beneath the ice that may have persisted for billions of years. Uranus and Neptune represent the ice giants, planets composed primarily of water, methane, and ammonia. Under extreme pressure and temperature conditions, Uranus rotates on its side with its axis tilted 98 degrees, perhaps the result of a colossal impact early. This extreme tilt creates bizarre seasonal patterns, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness. The planet's atmosphere appears remarkably featureless in visible light, but infrared observations reveal a complex system of cloud layers. Neptune radiates 2.6 times more heat than it receives from the sun, indicating an active internal heat source. Its atmosphere exhibits the fastest winds in the solar system, reaching speeds of 2,100 kilometers per hour. The Great Dark Spot was a massive storm system, similar to Jupiter's Great Red Spot, that appeared and disappeared during Voyager 2's flyby. Neptune's moon, Triton, orbits in the direction opposite to the planet's rotation, suggesting it was captured from the Kuiper belt. Its surface contains active geysers erupting nitrogen gas, and a crust of frozen nitrogen, methane, and carbon dioxide. The Kuiper belt begins beyond Neptune's orbit, extending from 30 to 55 astronomical units from the Sun. This region contains countless icy bodies, remnants from the solar system's formation. Pluto stands as the belt's largest known member, a complex world with mountains of water ice, glaciers of flowing nitrogen ice, and a tenuous atmosphere that freezes and falls to the surface. As the planet moves away from the Sun in its eccentric orbit, new horizons revealed a surprisingly active world, with evidence of recent geological activity, and a vast heart-shaped nitrogen ice plain called Sputnik Planitia. This feature likely formed through a massive impact and subsequently migrated to its current position, facing directly away from Pluto's largest moon, Charon. The two bodies are tidally locked, always showing the same face to each other. As they orbit their common center of mass, Charon itself shows a dark red polar cap, composed of tholins, complex organic molecules, created when methane interacts with solar radiation. Pluto's smaller moons, Nix, Hydra, Kerberos, and Styx, exhibit chaotic rotation patterns, tumbling unpredictably through space. Due to the complex gravitational influences of Pluto and Charon, beyond Pluto lie countless other Kuiper belt objects. Haumea spins so rapidly it has distorted into an ellipsoid. It possesses a ring system and two small moons. Makemake is reddish in color with a surface of frozen methane and ethane, while Eris is slightly more massive than Pluto, with a highly eccentric orbit that takes it nearly 100 astronomical units from the Sun. The scattered disk represents a population of objects with highly eccentric and inclined orbits that have been gravitationally scattered by Neptune. Sedna follows an extreme orbit, taking 11,400 years to complete one revolution. Its closest approach to the Sun is 76 astronomical units, while its farthest reach extends to 937 astronomical units. Such an orbit suggests the possible influence of an undiscovered planet, a hypothetical Planet 9 lurking in the outer darkness. The Oort cloud forms the solar system's true boundary, a spherical shell of icy planetesimals extending nearly a light year into space. Here the Sun's gravity barely maintains its dominance over the gentle tug of neighboring stars. Long-period comets originate in this frozen reservoir, occasionally perturbed from their orbits by passing stars or galactic tides, to fall toward the inner solar system. These pristine remnants from the solar system's birth carry clues about conditions in the early solar nebula. As we contemplate these distant realms, we recognize that our exploration has only just begun. New Horizons continues its journey into the Kuiper belt, while future missions are being planned to explore these frozen frontiers. Our Sun is a typical main sequence star, a G-type yellow dwarf in the prime of its life. It formed 4.6 billion years ago from a collapsing cloud of gas and dust, along with thousands of other stars in a now dissipated cluster. The Sun's energy comes from nuclear fusion in its core, where temperatures reach 15 million degrees Celsius, and pressures are 250 billion times Earth's atmospheric pressure. Under these extreme conditions, hydrogen nuclei fuse to form helium, releasing energy according to Einstein's famous equation E equals mc. Each second, 600 million tons of hydrogen undergo fusion, producing 596 million tons of helium. The missing 4 million tons are converted directly to energy. This process has continued for billions of years and will sustain our star for billions more. The Sun's interior consists of several distinct regions. The core, where fusion occurs; the radiative zone, where energy travels outward as photons; the convective zone, where hot plasma rises and cooler material sinks, creating the granulation pattern visible on the surface. Above the photosphere lies the chromosphere, a region of increasing the multi-million degree outer atmosphere visible during solar eclipses. The solar wind streams outward from the corona, a continuous flow of charged particles that permeates the solar system, creating the heliosphere that protects us from interstellar radiation. Solar activity follows an 11-year cycle, during which sunspot numbers rise and fall, and magnetic field polarity reverses. At solar maximum, the Sun exhibits numerous sunspots, solar flares, and coronal mass ejections. These events can disrupt communications and power grids on Earth, while creating magnificent auroral displays. Stars come in a spectacular variety of sizes and colors. Red dwarfs are the most common type, small cool stars that may shine for trillions of years. Orange K-type stars offer stable habitable zones and may be ideal targets in the search for life. Yellow G-type stars like our Sun are less common, but provide abundant energy for potential life. Blue-white O and B-type stars are massive and brilliant, but burn through their fuel in just millions of years. Their intense ultraviolet radiation makes life unlikely on nearby planets, but they play crucial roles in enriching galaxies with heavy elements. Binary and multiple star systems are common, with two or more stars orbiting a common center of mass. Some binaries are so close they transfer material between stars, creating spectacular novae and supernova. Variable stars change in brightness over time. Pulsating stars like Hiphides expand and contract rhythmically. Their period luminosity relationship makes them valuable distance indicators, while eruptive variables undergo sudden dramatic changes in brightness. As we contemplate the diversity of stars, we recognize that each type plays a role in the cosmic ecosystem, from the long-lived red dwarfs that may host the most ancient life, to the massive stars whose explosive deaths seed the galaxy with heavy elements. Stars are born within giant molecular clouds, vast regions of gas and dust that can span hundreds of light years. When a region becomes dense enough to collapse under its own gravity, the process of star formation begins. As the cloud contracts, it fragments into smaller clumps, each destined to become a star or brown dwarf. The collapsing material forms a rotating accretion disk that feeds material onto the growing protostar at its center. Jets of material erupt along the rotation axis, carrying away excess angular momentum. These Herbig-Haro objects can extend for light years, glowing as the ejected material impacts surrounding gas. When the core temperature reaches 10 million degrees, hydrogen fusion ignites and a new star joins the main sequence. The remaining circumstellar disk may form planets, asteroids, and comets, creating a newborn planetary system. The star's mass determines its entire life story. Low-mass red dwarfs burn their fuel so slowly they may shine for trillions of years, far longer than the current age of the universe. Medium-mass stars like our Sun spend about 10 billion years on the main sequence, fusing hydrogen into helium in their cores. When core hydrogen is exhausted, the star begins to evolve away from the main sequence. The core contracts and heats up while the outer layers expand. The star becomes a subgiant, then a red giant. For a star like our Sun, this phase will last about 1 billion years, during which the star will grow to 200 times its current size, engulfing Mercury and Venus and rendering Earth uninhabitable. In the red giant phase, helium fusion begins in the core, while hydrogen fusion continues in the surrounding shell. The star moves horizontally across the Hertzsprung-Russell diagram, becoming increasingly unstable. Eventually, the star expels its outer layers, creating a beautiful planetary nebula, while the exposed core becomes a white dwarf, an Earth-sized remnant that will slowly cool over billions of years. Massive stars follow more dramatic evolutionary paths. After exhausting hydrogen in their cores, they proceed through successive fusion stages, creating concentric shells of hydrogen, helium, carbon, neon, oxygen, and silicon fusion around an iron. So when the iron core grows too massive, it collapses catastrophically in a supernova explosion. For a few weeks, the supernova can outshine an entire galaxy, while creating elements heavier than iron through rapid neutron capture. The remnant core becomes a neutron star or black hole. Neutron stars are city-sized objects with the mass of the Sun. Their incredible density causes protons and electrons to merge into neutrons. A teaspoon of neutron star material would weigh billions of tons. Pulsars are rapidly rotating neutron stars that beam radiation from their magnetic poles, creating the appearance of pulses as the beams sweep past Earth. Magnetars possess magnetic fields 1,000 times stronger than typical neutron stars, capable of distorting atoms and producing starquakes that release tremendous bursts of gamma rays. When neutron stars collide, they create kilonova explosions that produce heavy elements like gold, platinum, and uranium, distributing these precious materials throughout the galaxy. Black holes represent the ultimate endpoint of stellar evolution, formed when collapsing cores exceed about 3 solar masses. Their gravity is so strong that not even yet they profoundly influence their surroundings. Accretion disks around black holes heat to incredible temperatures, emitting X-rays that we can detect across the galaxy. As we trace the life cycles of stars, we recognize our intimate connection to these cosmic processes. The elements that compose our bodies and our world were forged in stellar interiors and scattered by stellar deaths. We are literally made of stardust, brought together by gravity and cosmic evolution. Our Milky Way galaxy contains between 100 and 400 billion stars, arranged in a magnificent disk 100,000 light-years across. We reside in the galactic suburbs, about 27,000 light-years from the crowded center. Our location within the Orion Cygnus arm provides a spectacular view of the galactic disk, seen edge-on as the Milky Way band arching across the sky. The galaxy consists of several distinct components. The disk contains most of the star's gas and dust. organized into spiral arms where star formation occurs most actively. These arms are not fixed structures, but density waves that travel through the disk like ripples on a pond, triggering star formation as they pass. The central bulge is an ellipsoidal region of older stars that may have formed early in the galaxy's history. Surrounding everything is the stellar halo, a spherical distribution of ancient stars in globular clusters that may represent the galaxy's original building blocks. The galactic center is dominated by Sagittarius A*, a supermassive black hole containing 4 million solar masses. This gravitational monster normally consumes material slowly, but occasionally flares to life when stray gas clouds venture to. The observable universe spans about 93 billion light-years in diameter, containing perhaps 2 trillion galaxies, each with billions or trillions of stars. This vast expanse represents the portion of the universe from which light has had time to reach us since the Big Bang. The universe is expanding at an accelerating rate, a discovery that earned the 2011 Nobel Prize in Physics. Distant galaxies recede from us faster than nearby ones. Their light stretched to longer wavelengths in a phenomenon called redshift. By measuring this redshift, astronomers can determine both distance and recessional velocity. The expansion rate is quantified by the Hubble constant, currently measured at about 70 kilometers per second per megaparsec, meaning that for each megaparsec of distance, 3.26 million light-years, a galaxy's recessional velocity increases by 70 kilometers per second. The cosmic microwave background provides our baby picture of the universe. The afterglow of the Big Bang now cooled to just 2.7 degrees above absolute zero. This nearly uniform radiation fills all of space and comes to us from every direction we look. Tiny fluctuations in this background radiation reveal the seeds of all future structure. The slightly denser regions would eventually grow through gravity, forming the galaxy's clusters and superclusters we see today. The universe's large-scale structure resembles a cosmic web, with galaxies arranged in filaments and walls, surrounding vast cosmic voids. The Sloan Digital Sky Survey has mapped millions of galaxies, revealing this structure in ever-increasing detail. The largest known structure is the Hercules Corona Borealis Great Wall, a galactic filament spanning about 10 billion light-years. Dark energy comprises about 68% of the universe's energy content. This mysterious force drives the accelerating expansion, but its nature remains one of cosmology's greatest mysteries. It may be a property of space itself, or a new type of field that permeates the cosmos. Dark matter makes up about 27% of the universe, revealed through its gravitational effects on visible matter, but remaining invisible to all our telescopes. Ordinary matter, the stuff of stars, planets, and people, comprises just 5% of the total. The universe's age is precisely measured at 13.8 billion years, based on multiple independent methods. The oldest known stars in our galaxy are about 13.6 billion years old, formed just 200 million years after the Big Bang. The most distant known galaxy, G Unzi 11, is seen as it was just 400 million years after the Big Bang, already containing a billion solar masses of stars. As we push our observations ever closer to the Big Bang, We hope to understand how the first stars and galaxies formed, and how the universe evolved from its hot, dense beginning to the rich cosmic ecosystem we inhabit today. Dark matter remains one of science's most perplexing puzzles. We know it exists through its gravitational influence on galaxy rotation curves and gravitational lensing, but we have yet to directly detect a single dark matter particle. Numerous experiments search for this elusive substance. Deep underground laboratories like SNOLAB and Gran Sasso, shielded from cosmic rays by kilometers of rock, host detectors waiting for the rare interaction between a dark matter particle and ordinary matter. Particle accelerators like the Large Hadron Collider attempt to create dark matter particles in high-energy collisions, while space-based telescopes like the Fermi Gamma Ray Space Telescope search for indirect evidence of dark matter interactions. The leading candidates include WIMPs, weakly interacting massive particles, axions, and sterile neutrinos, but so far all searches have come up empty, leading some physicists to consider more exotic possibilities, or to question whether we need modified theories of gravity. Dark energy presents an even deeper mystery. Its discovery in the late 1990s shocked the astronomical community, who expected the universe's expansion to be slowing down due to the gravitational attraction of all matter. Instead, distant supernova revealed the expansion is accelerating, driven by some unknown form of energy permeating space. The simplest explanation is the cosmological constant, a property of empty space that causes repulsive gravity, but the predicted value differs from observations by 120 orders of magnitude, creating the worst theoretical prediction in the history of physics. Alternative explanations include quintessence, a dynamic field that evolves over time, or modifications to Einstein's theory of general relativity. On the largest scales, the cosmic inflation theory proposes that the early universe underwent a period of exponential expansion, driven by a different form of dark energy. This theory explains several puzzling features of the universe: its overall flatness, its large-scale uniformity, and the pattern of fluctuations in the cosmic microwave background. But we have yet to identify the field that drove inflation, or understand how inflation began and ended. The multiverse hypothesis suggests our universe may be just one bubble in a vast cosmic foam of universes, each with different physical constants and laws. While currently untestable, this idea emerges naturally from several theories of fundamental physics. The search for extraterrestrial intelligence continues, using radio telescopes to scan the sky for artificial signals, and optical telescopes to search for laser communications. The Drake equation provides a framework for estimating the number of communicative civilizations in our galaxy, but the values of most terms remain highly uncertain. From the fraction of stars with planets to the lifetime of technological civilizations, the discovery of even microbial life beyond Earth would revolutionize our understanding of life's place in the cosmos, while the detection of intelligent signals would fundamentally change our perception of ourselves and our cosmic significance. As we confront these profound mysteries, we recognize that not knowing is part of the scientific journey. Every answered question reveals deeper questions. The universe is under no obligation to make sense to us, yet through patience, curiosity, and wonder, we continue unraveling its secrets. As we conclude our journey through space and time, let us gently return our awareness to this present moment, to this room, this bed, your breathing body. We have traveled from the subatomic realm to the cosmic web, from the beginning of time to the universe's ultimate fate. Yet here we are back where we began, on our small, beautiful, fragile planet. The cosmic perspective can feel overwhelming, but it can also be profoundly comforting. All of human history has unfolded on this tiny world. Every joy, every sorrow, every achievement has happened right here on this pale blue dot. The universe may be vast beyond comprehension, but we are part of it. We belong here. We are the universe becoming aware of itself. The atoms forged in stars have come together to form beings that can look back at the cosmos and wonder about its origins. This capacity for wonder is perhaps our greatest gift. As you prepare for sleep, carry with you this sense of connection. You are not separate from the cosmic drama. You are an integral part of it. Let go of the day's worries. They are small in the cosmic scheme. Yet your experiences matter. Because you are the universe experiencing itself, allow your breathing to find its natural rhythm, inhaling the stardust that surrounds us, exhaling back into the cosmic flow. With each breath, release any remaining tension. Feel the weight of your body fully supported. The same gravity that holds the moon in orbit, that keeps the planets circling the sun, that binds the galaxy together, now holds you safely to the earth. The silence you hear is not empty. It's filled with the faint echo of the Big Bang, the whisper of spinning electrons, the hum of distant stars. You are swimming in a sea of cosmic vibrations. Let the images of swirling galaxies, distant nebulae, and orbiting worlds drift through your mind like gentle clouds. Don't cling to any particular thought. Allow them to come and go, like comets passing through the night. You are safe. You are connected. You are home. The universe will continue its slow, majestic dance, whether you are awake to witness it or not, so you can release into sleep, knowing you are part of something eternal. And when you wake, the stars will still be shining. The planets will still be orbiting, and the universe will continue its beautiful, mysterious expansion. But for now, let go and sleep.